Hi students, yep, I hope you have drawn something while thinking through for the past 3 to 4 minutes. Okay, so right now I'm just going to attempt to show you what you might be expecting. Okay, so again, let me just paste the structures over to the right hand side. Let me just push the arrow a little bit to the left. Okay, and right now I need to delete some of the arrows. Okay, probably I'd zoom a little bit so that it's a bit clearer what exactly is going on. Okay. Now, I'll do the blue one first, so probably you can just follow. Okay. So first of all, right, we are expecting the bonds between this Br and the set carbon to break, and then a bond between the Cl and the carbon to be formed. Okay, so I'll just put the Cl here. Okay. Now, you would expect the transition state, right, to be an early transition state. Okay, so if it's an early transition state, I think first of all, let let me just ensure that this is the BR. Okay, I'm just going to push the BR up a little bit. That signifies the bond breaks a little bit, and then because it's an early transition state and you are moving towards a product, so maybe this should come down a little bit as well, because it's going to be hybridized into sp3, correct? And this particular Cl, because it's an early transition state, I'm going to elongate all the way. Okay, let me just try to elongate. Yeah. Okay, you'll probably look something like this. This is a bit exaggerated, but yeah, you get the meaning. Okay, so I'm going to push this down a little bit as well. Okay, sorry, just not that one. I should actually push up a little bit. Yeah, rather than push down, because it's actually going to gain the or rather rehybridize into the sp3 hybrid orbital. Okay, so look something like this. Okay, now take note that this is a little exaggerated version of a transition state. Okay, we're not saying that this is the actual one. How it actually looks like, of course, we have to really study it in more details, probably through computational chemistry, but that's not the focus. But we are just trying to predict what it might look like. Do you realize that if I just push this up a little bit and this down a little bit, this thing looks a lot more like a chair conformation already? Okay, so I'm just going to just put the reaction arrows here. I'm just going to shift this to my left. Okay, and just try to draw the chair conformation out. Okay, and you notice that just now, if you remember what I said, the edge is actually projecting out towards you. Okay, so the edge is actually here. So the H is already so-called in a pseudo-equatorial position. So that's the term we use. And then this thing is moving towards a pseudo-axial position. So at the end of the day, the product we're expecting will be having both groups in the axial positions. Okay, so I'm just going to write it out this way. And then you might expect that from your earlier studies of conformation that, hey, this is not likely to be a product that is going to be very stable. So you might be thinking that, okay, then in that case, should we do a ring flip? Yep, of course it will do a ring flip. Okay, so upon doing a ring flip, you would expect the Cl to be here, and then the Br to be here. Okay, so this is likely to be the final product that we are looking at the end of the day. Okay, so after the ring flip. Okay, so my question to you is, if I'm going to get a product in the first instance, right, having both substituent in the axial position, is it likely to form then? Okay, the first thing that comes to your mind is probably not. Okay, you might be thinking probably not, because you'll be thinking that, hey, the transition state okay, has a bromo in the developing pseudo-axial position, and then the Cl, you know, kind of like not exactly developing, but it's attacking from far. So you might be thinking, this transition state, maybe it's not going to be very stable. Okay, that's fine. Okay, that's perfectly fine, because there's some logic in that. But you might want to hang on for a little while, because let us try to draw the other one first. Because if you try to draw the other one first, then you might end up with some surprise. Okay, so again, it's the same thing. I'm just going to nothing very inspiring. I'm just going to cut and paste the thing over. Okay, so yeah, just a lot of cut and paste here, and then just make sure the BR is here. So not going to explain much, but it's the same thing. So developing, this thing is about to break, and then the CL is about to form. I'm just going to paste the red CL over, and then okay, now, but this will look a little bit interesting. So remember, my BR is going to move towards a pseudo-axial position, so it's just going to move out a little bit. Okay, just a little bit. And then I'm going to push this carbon up a little bit as well. Okay, and then the Cl is going to the pseudo-axial position as well. So I'm just going to push it down a little bit here, and then I'm just going to push this down a little bit as well. Okay, it's a little bit too exaggerated, but yeah, okay, like something like this. Okay, now my question to you is, what do you think of this particular transition state? Yeah, what do you think about it? Does it resembles anything? It's definitely not a chair, if you're kind of agreeable. Okay, if I were to exaggerate this a little bit, I just push it down more. It resembles something you learn in chair conformation, but not exactly emphasized in our curriculum. It's actually called a twisted boat. So that means that if my red chloride were to approach it from the left hand side, you're going to end up with a twisted boat conformation as a transition state. Of course, you might be thinking, it doesn't really matter, right? Because at the end of the day, when the bond is formed, it will look perfect. I mean, you might be thinking that, oh, okay, when the bond is formed, it will look like this. And then you'll be thinking there's nothing seriously wrong, because you look like this, and then this thing will go up, and then this thing will come down, and then like it's probably not going to bother you a lot. Yeah, because at the end, you know that this is not stable, so it will undergo a quick ring flip. Okay, just a super quick ring flip to something like this. Okay, with the BR over here, and then the CL over here. Yeah, a very quick ring flip, you'll get that. And then you might be thinking that this is perfectly fine. Okay, but you might recall what we have learned in our curriculum, that the transition state is a very important structure, because if it's not stable, then why would it be formed in the first place? Or rather, why would the chloride wants to approach from that phase, from that side of the carbon in the first place? Okay, so this whole what I have explained earlier on, right? I hope you get to see that although when you draw it flat, it doesn't really matter whether you attack the first carbon or the next carbon, because the probability seems to be the same, right? But now, with a good understanding of conformational analysis and how the transition state looks like, right? I hope you realize that actually when the chloride approach from the right hand side or from the left hand side is actually quite different, because the transition state energy between the two are not the same. Okay, so in fact one is a lot more unstable than the others. So you get a twisted boat transition state versus a chair-like transition state. So although you have a developing axial bond forming, pseudo-axial bond forming, and in this case it's also developing pseudo-axial bond forming. So actually either way, you know, I won't say it's as bad, but it's equally having the pseudoaxial bond about to form at the same time. Okay, so in that case, the differentiating factor here will be a chair-like transition state versus a twistor boat transition state. Okay, so in that case, if I'm going to have a alkene cyclohexene conformation that looks like this, I would expect this pathway to dominate over this. Okay, so my question to all of you, and also a possible exercise you guys can do on your own would be, could you draw the same mechanism with the cyclic bromonium pointing down? Okay, see what products you get. Okay, look at the products you get, and could you also use this particular conformation to draw? So with up, cyclic bromonium up and cyclic bromonium down, and then you see the product you get. Okay, try to practice drawing it, and then at the end of the day, could you still make the same conclusion that you get a racemic mixture? So is the conclusion still correct? Okay, please think about it.